Welcome, ladies and gentlemen. Please give everybody the chance to join the web seminar. We will wait a little moment and then start right away. Okay, I think most people joined, so we can start now. Welcome together once again. My name is Mark Schinkel. I'm a technical project manager working for CIMAC. CIMAC is the leading globally non-profit organization for combustion engines. Today, we are going to continue our Tech Talk series with the topic controls and automation. We are going to hear two presentations from Mr. Brünnert and Mr. Schmidt. Today, our moderator will be Mr. Moore to guide us through the Tech Talk of today. Before we can start, I have to make some little hints. The first one, as usual, the legal hint that with this Tech Talk special, CIMAC would like to offer a platform for exchange. The presentations are an information offer of the respective author and or their companies, and thus do not necessarily reflect CIMAC's opinion. The second hint is that this session will be recorded. After the Tech Talk is finished, the presentation will be available on our homepage, cimac.com, under Events Tech Talks. Please give us a day time to afterwards place the video on our homepage. On top of that, I want to mention that you can feel free to ask questions in the chat. The questions will be visible to our moderators so that he can ask the questions to our speakers after the presentation is finished. Please also feel free to already post questions during the presentation and not just at the end. That makes it a little easier for our moderator to sort through the questions. During the talk, we are all going to be muted so that the speaker has the right to control the web seminar. And with that being said, I'd like to hand over the microphone to Mr. Moore.
Yeah, thank you very much, Mr. Schinkel. Also from my side, good morning, good afternoon, and good evening. And today we have the special topic of controls and automation. First, small information about my side. My name is Hinrich Mohr. I'm an independent consultant and involved in several CIMAC topics, especially regarding system integration and hybridization. And so I will chair these sessions. I'm looking forward to that and also to your questions. As already mentioned by Mr. Schinkel, we look forward to receive that. So let's start with the first presentation from Dr. Horst Brünnert from Schaller Automation about the prevention of sliding bearing damages by detecting mixed friction conditions with BureauMOS 2020. Mr. Brünnert, the floor is yours.
Okay, so thank you very much for the kind introduction. I hope my slides are seeable now. And we are very glad to have the opportunity today to present this topic that we have initially submitted for the CIMAC Congress. And the topic has already been mentioned. It's about sliding bearing damages and our BureauMOS 2020. As I said, we are very happy to be here at the Tech Talk special, and I would like to thank at this point also my co-authors, Mr. Flemmer from Schaller Automation, and also Mr. Maheinecke, Dr. Guzman, and Professor Jacobs from the Aachen University, who have contributed to this joint research in a public funded project. So my talk will be divided into the following sections. I will give you a very short introduction about us. Then we will look at the principle of our Baromos 2020 sliding bearing monitoring sensor. I will present you test rig results, which we have already presented in 2019, which are the fundament of the further research. I will then transfer that to the single cylinder engine results, which are the main topic today. And I will finally conclude, and of course, I will be happy to answer any questions later. Okay, so Schaller Automation is on the market since 1956, has been founded in Mannheim by Mr. Werner Schaller, and produced proximity switches, capacitive and inductive sensors, and went then into the large engine market in 1967 with the launch of its first Visatron oil mist detection system. And as you can see here on the time rate that we have continuously improved our portfolio here for the oil mist detection up to 2020, where we introduced our latest version. We have now more than 55,000 engines equipped with the oil mist detectors and are roughly 100 employees worldwide, with the R&D center here in Germany and 4 camp centers. And we also introduced in 2018 our first condition monitoring product, which is the Acomos here, a 3-axis acceleration monitoring system able to detect vibration anomalies. And what we are talking today about is the Baromos 2020, our bearing monitoring system, which we have launched in 2019. So far for the introduction. Let's go now to the motivation for the sliding bearing monitoring. I have put together some data from the marine insurance company, the Swedish Club. What you see here is data from 2015 to, okay, sorry. Okay, I'm sorry. So I hope this audio is now back again. Okay, so yes, what I show here is the, sorry, now I'm completely lost here. No, okay, again. So we have data from the Swedish Club from 2015 or 2004 to 2017, basically from the auxiliary and main engines. And we still see that the bearing damages have the highest contribution and financial impact to machinery failure still. And that is due to the expensive repair and downtime you have when you have a crankshaft damage. And you can also see that you have an average cost of roughly $1.8 million per claim if you have such an incident. So it's still a very important topic, as we can see from this data. What is Schaller doing in this context? Well, of course, the oil mist detector is the last gate in order to avoid an explosion, which is the consequence of a bearing damage. So by detecting oil mist, which is generated at a hot spot because lubrication oil is evaporated, we prevent an explosion. And if you are able to detect the reason for this hot spot, which is basically a metal-to-metal contact and therefore a frictional contact in the sliding bearing, and then you are able to have a very early indication of the damage initiation. That is the basic idea of our Baromos sensor, which I explained in the next slides. Of course, you can also have the chance by detecting vibration anomalies in order to even get an earlier indication. However, vibration signals, of course, are very broad normally, and it's difficult to identify where they come from. But in condition to our Baromos sensor, you can get more information in order to increase the prevention corridor afterwards. And that means you have a chance for going from corrective, preventive maintenance activity onto a condition-based predictive maintenance strategy. Now, our sensor, as you can see here, the Baromos 2020, is connected to the end of the crankshaft. And the idea, what it uses is the so-called Seebeck effect, which is a physical effect where a thermal electric voltage is generated once 2 different metallic materials are getting in contact to each other and having different temperature levels. I will explain it in a short while. Basically, if you look at the Sobert's feedback curve, you see that the coefficient of friction over sliding velocity gives you an idea on what is the operation the state of such a sliding bearing. In normal operation, which we call hydrodynamic operation, you have enough lubrication oil thickness here in or between the two moving parts, the shaft and the bearing. Once you get a contact between the metallic surfaces, you enter the mixed friction regime, and this finally ends up in the solid body contact, of course, then generating metal-to-metal contact heat, and in the consequence also generation of oil mist. So if you are able to have an online detection of the transition from the hydrodynamic operation here into the mixed friction, you have a key to condition-based wear evaluation. And that is what this sensor can basically do. If you look here at this principal sketch, you see the crankshaft down here, and you see some representation of a multi-layer bearing, in this case main bearing. We have a contact here in case the lubrication film is gone. We have different so-called Seebeck coefficients, different temperatures, and as you can see here, the thermal voltage is then proportional to the difference of these material-specific constants and the temperature difference. The electrical circuit is only put together in this case that the contact is established. So on the one hand, our Baromos crankshaft adapter is directly connected to the moving crankshaft. Internally, it's isolated to the housing, and the housing of our sensor is connected to the housing of the engine. So as I said, this thermoelectric voltage is only detectable if you have a contact in here. And that, in fact, allows us to evaluate the lubrication state in the contact and to detect mixed friction states. So that's the idea for the early verification. Let's look at the details or at some results from the test rig results. Don't be shocked, so I will explain you this slide very fast and easily. We have evaluated different wear conditions, so light wear, severe wear, and significant wear like thermally induced failure. On the test rig in Aachen at the university, we then introduced a load in terms of a pressure, of a hydrodynamic pressure in megapascal, and we also decreased the sliding velocity by decreasing the RPM of the test rig. Therefore, you can set a point where you go from hydrodynamic lubrication into the mixed friction point here at time 0. It can be seen here in the coefficient of friction and in the frictional power loss as well, that you have here to change. And what we monitor on the bearing is the temperature and, of course, the thermal voltage. And what you see here for the severe wear condition, that you have a very fast and instantaneous reaction of our thermal voltage and a little bit smaller increase of the temperature sensor, which takes a little bit longer time. This is what we see in all of the experiments. So if we go to the thermally induced failure, which is a much severe damage and degradation of the bearing, you have a higher pressure here, higher load. We decrease the sliding velocity to a critical value, and also at the point 0, we get a change from hydrodynamic lubrication to mixed friction. We see that again in the coefficient of friction and in the frictional power loss, and finally also in the thermal voltage and in the bearing temperature. Again, the thermal voltage is very fast and instantaneous, and also you can see here, due to the signal length and also how it looks like, you can differentiate between a light, severe, and a thermally induced failure. Again, also the temperature sensor, of course, reacts to this, but as I said, what we see is that the thermal voltage is always much faster and sensitive in this varying temperature response. So now the key was, or the idea was, to translate it to real engine operation. So test rig results are one thing, but is it really suitable for an engine operation? So as we don't have a real large engine in terms of a single cylinder test bench, we made a scaled trial with a Hutz single cylinder engine, which is from the basic design comparable. We detected the main bearing temperature and also our thermal voltage Baromos, together with engine parameters like RPM, power, temperatures, and also pressures. And you can see here the real test setup on this engine where the Baromos is connected to the end of the crankshaft. This is put together on a test bench control where we can log it and evaluate it. From the test program, we always started with a new main bearing. We assembled it. For that, we make a measurement of position, shape, and surface. Then we start a running-in procedure for about 50 hours of operation at 4 kilowatt load and 1500 RPM. We then disassemble the bearing and repeat the measurements. After that, we reassemble the bearing, start a damage experiment. We do that by plugging a lubrication bore in order to generate efficient lubrication. Operate it in this condition, disassemble the bearing, and repeat the measurements again. And finally, we made a really hard damage experiment, I would call it, where we forced a seizure of the bearing by assembling here the bearing into the flange in a tightened position. And again, we used here a new bearing, introduced this tightened assembly with the deficient lubrication, and then we evaluated the signals. So what do we see? If you look on the graph on the right side, we have three measurement parameters that we evaluate. First of all, the roughness, so as an indication of the surface, the diameter change as an indicator for the deformation of the bearing, and the roundness as an indicator for the shape deviation. What you see is first in the running in, which is normal, that the roughness is decreasing a little bit. That is due to a smoothing, because now the peaks of the surfaces are getting in touch with each other, and after running in, the surface is more or less smoothed in. If you introduce the deficient lubrication, however, you see that you have a significant increase in the surface roughness. You have a diameter change significantly, which is indicating the bearing deformation. And you also have a change in the shape of it, so the roundness increases as well. So we see that this is an indication for a wear due to deficient lubrication. And I'm sorry that it's so small now, but you can believe me, what you see here is that the second layer of the bearing is already visible, so we have an obvious indication of wear. So in the thermal voltage, we start with the running in. How does it look like? You see for the first startup of the engine with a new bearing, you have for roughly 10 minutes maybe a mixed friction here. The normal operation is in this case at around 80 microvolts, plus minus 10 microvolts. So once you exceed this regime, you can surely detect mixed friction. This is a normal operational state for every running in that we observe also in field tests, because as I said, first of all, the sliding bearing contact is getting contact with each other, it's moving in. After that, and we are running that for 50 hours and by several days, you only have very short mixed friction for maybe 1 or 2 minutes when the engine is starting up because of the shaking of the engine. However, this is also very important to know, because if you have a sensor, you need a software that can actually differentiate between normal mixed friction, like in startup and in running in, and also mixed friction states which lead to continuous wear and degradation of the bearing. Then let's look at the damage experiment. So as I said, we have deficient lubrication, the crankshaft lubrication bore is clogged. What happens is, let's start down here with thermal voltage. You see for 40 minutes significant mixed friction, and what interestingly happens is after that it goes back into hydrodynamic operation. This is due to an interesting fact of our Hutz engine, because due to the movement of the parts inside, you always have a parasitic lubrication. So what we detected is that you cannot damage the bearing so far that you have a catastrophic failure on it, but indeed it will sometime return to the hydrodynamic operation. In the main bearing temperature sensor, at the same time, you see that during the warming up of the engine, you can see that at the oil cylinder and exhaust temperature, it's mainly following, of course, the warming up, but it does not see a difference due to the mixed friction. So no indication of this wear condition. So we can say that even in this light wear conditions already, the signal here in Veramos is sensitive and present for over 40 minutes, which you can evaluate. Now, as I said, as we could not destroy the bearing the way we would like to do it in this damage initiation experiment, we forced a severe wear by having a tightened assembly of the bearing and also using deficient lubrication again. We started the engine 3 times, you see it down here, and you see that you have a severe mixed friction in amplitude, but also in the shape here for roughly 30 seconds. After 30 seconds, the engine stopped operating because of the seizure. We repeated it 3 times in order to get an idea of that is repeatable, and in fact it is. However, after 3 times of starting up, we stopped this experiment because we risked to damage the crankshaft, which you can also see at the main bearing temperature sensor. Of course, due to the seizure and the hard metal to metal contact, also the main bearing temperature sensor sees a signal increase, and also you can see here with temperature rise, which is dangerous for our main bearing then, of course. Okay, so let me conclude and sum up. What we see is, first of all, we can transfer the findings from our test rig results to the single cylinder real engine operation. We can use the monitoring of the thermal voltage with Baromos 2020 as a fast, sensitive and repeatable tool for the detection of mixed friction, as the experiments showed. We see that the evaluation of the duration in mixed friction can be used for the prediction of remaining lifetime of the affected sliding bearing. So this can be evaluated and put into a predictive tool. We also see that there is potential for signal evaluation, which allows for the differentiation between light and severe wear conditions up to thermally induced failure. And Baromos 2020 can also be implemented then as a final result and used for a predictive maintenance tool in order to prevent sliding bearing damages. And to sum up at the end, you can see on the right side some real installations on multi-cylinder field test engines in marine applications, but also power plant applications. And with that, I'm coming to the end of my presentation. Thank you very much, and I'm happy to answer any questions. Thank you very much.
Yeah, thank you very much, Mr. Brünnet, for your interesting presentation. Let's come to the discussion. Again, I'd like to ask also the audience to place some questions. Let me start with one. In chart number 6, you had a nice graph where you showed different occurrences before a bearing damage, and yeah, maybe if you go there, yeah, exactly. And based on your current investigations, do you have an idea what time periods we are talking about between each occurrence?
Yes, in fact, we have the one thing is that we have to think about, of course, is about the scale of the experiments. So on the test rig, we use normally 30mm bearings. That means if you have a good position for the main bearing temperature sensor, for example, and also the Baromos sensor, then you get very quick results for both sensors. But if we go to other experiments and also from field experience that we have, we see that the first signal evaluation of the mixed friction already starts some hours before then actually a deformation or the contact is good enough in order to have an increase in the main bearing sensor. So if you think about the real skate bearings, of course, it takes much longer time to bring the heat to the bearing sensor, and it depends on the position. And then if you only have small contacts, as I presented for startup and other mixed friction states, of course, maybe the sensor cannot react at all. But the thermal voltage gives you a very sensitive idea on when this event really happens. So yes, from the test rig results, we can talk from minutes until the difference between thermal voltage and temperature sensor increases. And if you think about the evaporation of lubrication oil, which is about 280 degrees maybe, of course you have some more time. So it will be at least 1 hour or more that you increase the prevention corridor. And if you have only light wear, for example, you can have even days. So that's the idea on how to calculate the remaining lifetime out of the duration in mixed friction.
Yeah, thank you. Coming back to the temperature, you mentioned that the bearing temperature. I know from the field that typically engines are equipped with temperature sensors, but they are typically connected to the backside of the bearing, and so typically they are quite slow in reaction time. What if we could have a temperature sensor in the bearing shell? Would this then be the first detector of such events? or would you see first vibration, or your thermoelectric effect?
It will be definitely faster, that's for sure. But as I said, once you get the first contact between the first, I would say, surface roughness peaks, the barometer sensor is already able to detect it. So we have the ability to adjust the sensitivity, of course, as well, because we don't want to be too sensitive. But there is no temperature increase when you have a small mixed friction. So the thermal voltage will always be the first signal before the temperature sensor even have the chance to detect it.
Okay. So let's look on the questions. There is one. With BIROMOS 2020, is there a way to identify the position of the faulty bearing in a multi-cylinder engine? For example, crankshaft bearing number or crankshaft main in relation to crankshaft main bearings in total?
Yes, this for the sensor itself, it will not be directly, but if you connect it to the ECU of the engine and you compare it with the firing sequence, or you have a cylinder peak pressure sensor, for example, you can have a location of the bearing where the signal comes from.
Yeah, okay. Thank you. Next question. Is the sensor approved by marine classes for use in preventive maintenance procedures?
Yes, with this sensor, we did the first time a mutual recognition certificate, which we have to renew this year. And therefore, it means it is for all IX classes approved, yes.
Okay. Thank you. Then the next one, on a multi-cylinder engine, is there a way to know if more than one bearing is suffering accelerated wear and distress, and which ones are suspect?
Yeah, that's the comparable question to the one before. The main principle gives you only an idea about mixed friction in the whole crankshaft bearing chain. But as I said, if you combine it with the firing sequence and an additional sensor, you can identify the location. But from the BIROMOS sensor itself, you first only have an idea about the complete behavior of the, I would say, the drive chain from crankshaft and bearings.
Well, I understood the question in a way that if not only one bearing suffers a failure, but more than one, would it be possible also to have the this information?
It would be possible, but you would have to have an, again, it also depends on the firing sequence, because you can then calculate on which position you expect a signal. Because what also happens, BIROMOS has an RPM sensor inside. And if you can link to the firing sequence, you can at least identify and which position the signal has to come from. And therefore you can also say, okay, that this is one bearing or more bearings, yeah.
Okay, thank you. What is the lower size limit you envision for this product? Is there a crankshaft diameter lower limit when this works?
I wouldn't say that, because what we saw, the crankshaft adapter, it is always, of course, produced according to the engine, and what we only need is to transfer the moving to the internal of the sensor. But it's nothing more than you enlarge the crankshaft. So as you see we have adapted it on the Hutz single cylinder engine. So this is an engine, maybe, I don't know, in the size, really small size, which is for very small stuff. Yeah? So I don't think that in the smaller regions it's also adaptable.
So this means also from the engine size, it can be adapted to all kind of engines. So independent if it's a high speed, a medium speed, or a low speed engine.
Yes.
So from the smallest high speeds even to the biggest two-strokes.
Well, from the two-stroke, I have to say we don't have experience yet on the two-stroke engines, but the main experience is done on four-stroke engines so far. But for four-stroke engines, it only depends on how much space you have left to adapt the sensor. So if you have a lot of different components at the end of the crankshaft or interfering geometries, of course, that could be difficult. But so far, we have managed to adapt it to all engines that we have field tested, or that people came to us and asked us to adapt it. But we would have to evaluate it on a case-to-case basis, of course.
Well, in a two-stroke engine, you have typically other bearing material. So compared to a four-stroke engine, so maybe this have an impact as well.
Yes, and that's also something that we have evaluated in this public funded project. I couldn't show those results. We have looked at different materials, 5 different materials, in order to see how the thermal voltage changes actually, because as I presented, the Seebeck coefficients are material dependent. So you can have a negative or positive thermal voltage, but what we see is that it establishes always to a certain level corresponding to the materials used. So there is always the chance to detect it. Of course, at least it must be electric connector. So if there would be, which of course a large engine is not used, but there are applications where you have for PTFE bearings or something like this, then the principle will not work.
Okay, yeah, of course. So then here's another interesting question. Is the system also able to detect gudgeon, piston pin, and Conrod big end bearing conditions?
We are actually, that's one of our newest research topics, the big end bearing. The evaluation path is a little bit different, yes. But this is also possible. We made a proof of concept already, and we are also preparing a paper for the large engine conference in Rostock as well for in September, and there we look at also results for a big end bearing evaluation.
And this is going to be done by the same sensor on the crankshaft?
Yes.
Okay, very interesting. Yeah, thank you very much.
You're welcome.
Yeah, Mr. Brünne, thank you very much for your intensive question answering. And then I would say let's go for the next presentation. So then I invite Dr. Schmidt from Awad Automation. There he is. To speak about combustion control based on low-cost vibration sensors for variable fuel auto engines. Mr. Schmidt, please.
Mr. Moore, thank you for the introduction. Can you hear me and see my screen?
Yes, very well.
Yes, okay. So ladies and gentlemen, welcome to my talk on you can see the very long title about combustion control and different things. And maybe first of all, we have to break that down to the real topics. So it's combustion control, vibration sensors, and something about variable fuel. So the main topic is the vibration sensors. This is some result we have worked out in a research project together with the University of Karlsruhe. We need the sensor information to do combustion control. I will explain what kind of control, and this will be especially necessary when fuel composition changes or when we have to deal with different fuels in the future. So I'll start with the variable fuel application, show you some results on regarding hydrogen mixtures with natural gas. Then we go to combustion control, and finally the role of the vibration sensors. But maybe first of all, what kind of engines are we talking about? So Awad Automation in Germany, we are developing and manufacturing control systems for four-stroke gas engines or engines developed from gas engines. So dual fuel engines for marine applications as well. These engines range from maybe 50 kilowatt is a very small engine for us. So this is the smaller class, and it goes up to 20 megawatt engines in different applications. It's always power generation. For the smaller ones, it's stationary power generation. And for the large engines, we have many applications for auxiliary power generation on vessels, but also electrical power generation. I've grouped these classes to 3 groups. The smaller ones, stationary applications with gas, mainly natural gas, but also the typical special gases like biogas or landfill gas, sewage gas, mine gases, synthetic gases, things like that. And for the blue marked gases, we are dealing for a long time with fuel variations. So the compositions of these gases always change, and control systems may have to react to these changes. The second class, between 300 kilowatt and 3 megawatt, is just the same application, but one difference for the talk today is that maybe for a 3 megawatt engine, you may start to think about expensive sensors, because you've got a costly engine and it's worth a lot. So you can, for example, spend money for cylinder pressure indication systems on your engines. You will probably not do that for the small ones. For large engines, beginning from 5 megawatt, cylinder pressure systems are quite established now, and it's worth the information. We'll see that during my presentation. Here we have the specialty kind of different gases. We're controlling a lot of engines powered by LNG gas, and we're talking about the future fuels like methanol, ammonia, fuels that will be produced from renewable energy in the future, maybe also pure hydrogen systems. So the topic about the fuel is now, we have the big question at the moment: what will be the fuel of the future? We have currently a major fuel is natural gas or in form of LNG. We are currently talking about increasing the amount of biomethane, talking about methanol and ammonia and hydrogen, and maybe also of mixtures of these. For example, when you think about an ammonia fueled engine, it might be necessary to put some hydrogen in to make the ammonia burn well. So we think that the winner of these fuels, well, it's just unknown. I can't tell you today. But this means that for control systems, and our part is the control systems, in the future we will have to deal increasingly with variable fuels or variable fuel compositions. There will be more fuels and there will be more mixtures possible of these fuels. So the effect of the fuel on the combustion is clear. The fuel is the thing that is combusted, and I can show you some properties of the combustion with an example of an engine that we had on a test bed. It's a 400 kilowatt gas engine, natural gas engine, and we added hydrogen to see the effect on the combustion. What we see here is one experiment. It lasted about half an hour. We started with natural gas only here at rated power. This is the 400 kilowatt electrical power. And then we step by step increased the hydrogen content. So here on the left, we see the share of the hydrogen content. 0% is just 100% natural gas. Now, when we have a look at the combustion properties, we start with the center of combustion. Center of combustion is the point during the working cycle where half of the fuel is burned. And for the natural gas case, here we can see in this engine, in this case, we have a center of combustion at about 9 degrees after TDC. And if we increase hydrogen step by step, 10%, 20%, and up to 30%, this is volume percent hydrogen, we can measure the center of combustion, and we see that the center of combustion moves to smaller values. So here we are at 6.5 degrees after TDC. So this means that 30% hydrogen shifts the combustion by about 2.5 degrees crank angle. 2.5 degrees is a lot for an engine. We can see that with other characteristics as well, but it makes a big difference whether the center of combustion is at 7 or at 9.5 degrees after TDC. Earlier combustion, it's clear it also may lead to knocking combustion in a gas engine. So for the same measurement here, we have counted the knock events starting with natural gas. We see there are no knock events in this engine. Then we increased the hydrogen amount, and we can see that the number of knock events increases. So this is just the number here. It's not the strength of the events, only the number. And at the end, we had to stop the experiment because knocking was too strong. So we had to shift ignition timing then and continue with more hydrogen. But what you can say is that, of course, hydrogen increases knocking numbers in this engine. There are other combustion characteristics we can measure. For example, how long does the fuel need to be converted to electrical energy? So again, same measurement, we see that by adding 30% of hydrogen, we shorten combustion here by about 2.7 or almost 3 degrees crank angle. And during the measurements, we have seen that this is mainly in the second half of the combustion. So first half is almost independent from the hydrogen amount, and the fast combustion comes in the second half. 2.7 degrees crank angle compared to the 26 degrees for the complete combustion is about 10% faster combustion. We can also have a look at the maximum firing pressure induced by the hydrogen, and it's clear earlier combustion and faster combustion leads to higher max pressure. In this measurement, the hydrogen increased the max pressure by about 10% compared to the nominal pressure. So, of course, it's clear that the fuel has one of the main influences on the combustion properties. And for me as the control system developer now, the big question is how can we measure and how can we control these combustion properties during engine operation? So not on the test bed, but for the field engines. And combustion control is, of course, a wide field of topics. What do I note under combustion control or engine control? The task on the engine is, we have here an example of an engine with central gas mixing, throttle valve, and then here, typically for our engines, it's 6 to 20 cylinders, inline or V engines. And the engine control system has to control the actuators, for example, the gas mixer, throttle valve, the ignition timings, anything that can be controlled on the engine. It's not only speed and load and emission control. So this is, let's say the core control functions. Also something like anti-knock control or misfire detection and control, cylinder balancing. If you have some information about the single cylinders, I can show you an example for that. These are real control functions, but the engine control system has more tasks. It has to protect the engine, which means avoid damage, avoid or react to misfire, knocking, pre-ignition, avoid too high maximum firing pressures and such things. And of course, because the control system has all the data, the live data about the engine, it can or it should provide an interface to condition monitoring systems. So to be able to maybe predict damage, we have seen that in the Schaller presentation before, or to conclude something about aging of the engine or about aging of engine components. Now, to do all this, we need sensor information, and one example, what we could control if we had sensor information, is something I can show here. This is an example of a 200 kilowatt gas engine, natural gas engine, in a CHP application. And we can see the effect of cylinder balancing. So we did control the centers of combustion of all 6 cylinders of this inline engine, and controlled them to the same desired value. On the left side of this plot, you can see an uncontrolled case. So the centers of combustion are strongly different from each other. These are 6 curves for 6 cylinders. We also plotted the NOx emission, because in this research project we concentrated on NOx emissions. Then we switched on the control, the cylinder balancing control. We can see that in the mean values of the 6 cylinders were driven to the same values, and we can also see that the NOx emissions went down significantly. So by switching on here in this application, cylinder balancing of centers of combustion, we could reduce NOx emissions by between 5 and 10% in the rated power case. But of course, to be able to do something like that, we need the sensor information. For example, here, in this case, center of combustion of the different cylinders. Now, if we have this information, we have some sensor information about the combustion, then we can provide this to the control system, and the control can do its tasks: control, protection, and maybe data interface. Now, you all know what kind of sensors can be used here. If we want to know something about combustion, then we can use cylinder pressure sensors. I'm not talking about cylinder pressure sensors today, but this is maybe, I put it here, a perfect solution for that, because then we directly measure the peak firing pressure. We can calculate the power output of each cylinder in the engine. We can calculate the start of combustion, center duration of combustion, see misfire events, knock events, and many things more. So if you have a cylinder pressure sensor in your cylinder combustion chamber, then you know almost everything about the combustion. One solution, but I put it also here, it's maybe only technically the perfect solution, because it's also quite expensive. And this expensive means it's not only the investment for the sensors, which would be the CAPEX cost, it's also during operation. Durability might be a problem sometimes for the cylinder pressure sensors, because the environment is very harsh inside the cylinder. And if you have to exchange sensors for each of your 20 cylinders in your engine every 2 years, this is also quite costly. And therefore, of course, the question is, can we use some other sensors to get the same information that is usually provided by cylinder pressure sensors? And well, title of the presentation is Vibration Sensors. Therefore, we can suppose that it is possible. And I will show you some results now. Vibration sensor means it's just a standard knock sensor. This is a picture of a Bosch knock sensor. These knock sensors are a real mass product from automotive industry, so not really from large engine, but from the small automotive ones, and they are really cheap regarding the cost for CAPEX and for operation. Usually you will never exchange your knock sensors during the lifetime of the engine because they are outside the engine, so there's no real problem with aging. They also show high dynamics in their information. We know that we use them for knock detection for each working cycle in each cylinder. It's possible. But the big question now is, can we use these sensors to get more information from the signals? Knock detection and also misfire detection are standard information provided by these sensors. And it would be very interesting, of course, if we could also compute these combustion characteristics like start of combustion. This is SOC here, center and duration of combustion, or of course, maximum firing pressure, power output of each cylinder. If we could compute this from vibration signals, would be a good thing. And this is something we have examined in a research project together with the University of Karlsruhe, the Institute of Professor Koch in Karlsruhe. This is a picture of the CHP plant where we have done the research project. So it was a real engine, fuel engine, full engine, not single cylinder, an MAN engine with about 200 kilowatt electrical energy. We also Always look at the thermal energy because this plant is used for heating the buildings at the university. So it's a kind of combination of a real CHP plant and test bed equipment in that plant. The project was sponsored publicly by Deutsche Bundesstiftung Umwelt. There's also a project report regarding the project. So if you're interested in that, you can of course contact me and I can provide you these results. In this research project, we have firstly examined that MAN engine, and we started with the influence of the knock sensors or vibration sensors themselves. So we examined sensor types and sensor positions. I will not go into detail for that. There's some information in the report. But regarding sensor types, we can say that the standard knock sensors are perfectly okay, not only for knock detection, but also for, I will show you at once, the combustion calculation. In the project, we have examined some more sensor types, very expensive ones with quite good sensitivity or a wide range of frequencies, but it's not necessary. So the standard knock sensors are okay for this task. Regarding the sensor position, things become more difficult. The sensor position of the vibration sensor has a very strong influence on estimation quality. We know that from knock detection there, it's also important where to place the knock sensor, but usually you will find a position so that you can detect knocking in each cylinder. Regarding the computation of things like max firing pressure, center of combustion, there is a stronger influence with the position. And the position, well, of course, depends on the engine type. So for this MAN engine, we have found very good sensor positions for the task we had to solve. But if you ask me whether I just can transform this to your engine, I have to say, well, we have to look at that. Usually, I would start with the standard knock sensor positions. So in this case, they are pointed here on the right side. These are the standard knock sensor positions provided by MAN. We also started with them, but we have put some more cylinders on that. On the cylinder head, we also put some sensors on at the bearings of the crankshaft. And we compared all these signals with regard to the combustion properties. And we have found some better positions than the knock sensor positions on this engine. On the second engine was the same. And in this example, then I can show you some measurements afterwards. For combustion sensing, we used 3 vibration sensors. The first one between cylinder 1 and 2, second one between cylinder 3 and 4, and then the third one between 5 and 6. So we had 2 cylinders measured by 1 sensor. But sensor position is a topic. If you want to apply our method to your engine, then you or we will have to discuss about that, how to find a good position. Now, if we have a look at the results, how good can we estimate the properties of combustion? I just showed it. We use 1 knock sensor per 2 cylinders. So which means for the 6-cylinder engine, we had 3 knock sensors, put them outside the engine. And of course, in the CHP plant, we also had the in-cylinder pressure sensor as a reference signal. We need that to calibrate the estimation for this type of engine. Now, in a scatter plot, when we compare the real center of combustion, so real means this is measured by cylinder pressure sensor. It's on the horizontal axis here on the right, COC, center of combustion. And we put this in relation to the estimated value. So here on the vertical axis, we have the center of combustion estimated from the sound signal or vibration signal. Then we can see that this is almost a perfect diagonal in this scatter plot, which means if the real center of combustion of 1 working cycle is at 5 degrees after TDC, then our estimate is also at 5. The different colors here in this plot mean different operating points. I think this is operating points from a measurement lasting about 60 minutes in 1 cylinders, and each dot in this plot represents exactly one working cycle in the cylinder 4. So this is per working cycle, very precise estimate of the center of combustion. If we put a plot like that, not in the form of a scatter plot, but over time, so here for the other cylinder, cylinder number 3, same sensor, but the other cylinder, a different measurement, it's about 45 minutes here. In this experiment, we changed the ignition timing of cylinder number 3. So with the ignition system, we did variations of the timing of the spark plug by about 5 degrees crank angle. And then we measured the resulting center of combustion here with the cylinder pressure sensor and compared this again to our estimate. And here in this plot, we can see that, well, we can see nothing because we have in blue, here ZD ref is the real measurement, and the other blue line is the estimate, and it's just the same curve. You cannot see any difference here. The estimate is too good for this pair of cylinders 3 and 4. If we plot the estimation error, this is the orange line down here, we see that it's almost constantly 0. And the maximum error, so the worst working cycle during this measurement, and the maximum error between estimation and measurement this was half a degree crank angle, which was a surprisingly good result. We did not expect that. We thought, well, maybe it's possible to be by 1 or 2 degrees exact, but we are far better with the vibration sensor here. This means that regarding that big question about the information content delivered by a vibration sensor, well, we can obtain perfect results. We have proved that for the center of combustion. We also have done some comparisons regarding the maximum firing pressure, power output of each cylinder, duration of combustion. I'd say we had good results. They were not as perfect as for the center of combustion, but in our research project, we concentrated on emission reduction. And because the center of combustion has a very direct or straightforward influence on the emission, we optimized our algorithms with regard to the center of combustion. I think it should also be possible to have similar results for other combustion characteristics as well. So what we obtained at the end is that for all these control tasks in our system, we can close the control loop, not only through the in-cylinder pressure sensor, but also through a vibration sensor, means typical NOx sensor. After the NOx sensor, here we have the electrical signal, and then of course we need some software to estimate that combustion information. Estimate because some sensor is outside. We do not measure the combustion. We measure vibration, and then we have to do some estimation of the combustion information. To sum up, I can give some comparison of the two principles. Either the in-cylinder pressure sensor, which of course is best if you can afford or want to afford these sensors. You cannot have more information during engine operation, but there might be some alternative for some size of engine or for some applications where you do not really need that high information content, or you do not want to pay the price for it. There is one major difference regarding the principle. With in-cylinder pressure sensors, we do real pressure measurement. We measure the pressure in the combustion chamber. The vibration sensor does an estimation. So there is some kind of software algorithm in between, which is very important. So the key element in this method is software compared to the key element in the in-cylinder pressure chain is the hardware. It's the sensor. It's the most important part there. Of course, the information quality in the vibration sensor is not as good as in the pressure sensor case, but I've shown you the results. I think this is, we can do a lot of control with this kind of information quality. Cost, it's clear, mass product, very robust. There's one interesting thing that with a NOx sensor, which is mounted outside the engine, we do not really need one sensor per cylinder as in the pressure case. In the best case, it could be sufficient to have one sensor for the complete engine. Maybe for a 6-cylinder engine could be possible, but so we have examined 2 different engine types, and for both of these 2 types, we ended at 1 sensor per 2 cylinders. The key issue in our method is, I said it, the sensor position, and that this position probably is engine type specific. So this needs some work to find the good position on your engine. Key issue with the pressure sensors, I think, is sensor robustness. And one more interesting point could be the mounting. Of course, the NOx sensor is outside, but this might make some retrofit solutions possible. For retrofit of cylinder pressure, well, it's difficult because if you have to machine the cylinder head to put the sensor in, this is quite expensive. So it could be much more simple to add a vibration sensor if you have a field population of engines that you want to improve regarding combustion. So I'm at the end. If you have any questions, I'll try to answer them, or if you are interested in the report or further discussion, please contact me.
Yeah, thank you, Mr. Schmidt, for this interesting presentation. And so the first questions already came in, and let's start with the first ones. You mentioned in your title and also in your presentation, or you considered Otto cycle engines. Do you think that this principle would work on a diesel cycle engine as well?
I think so, yes. Because when it comes to dual fuel engines or also the methanol or ammonia engines, we're discussing about the principle Otto or diesel, and maybe it's then some kind of mixture between these. Pilot fuel is a diesel and ignites the Otto cycle. So the main thing is the sound that is transported from combustion to the outside position where the sensor is. And therefore, I think it could also be worth regarding diesel principles.
Yeah, I think you mentioned that already. That the signal when you have a cylinder pressure signal and the vibration signal, this is completely different from each other. One is the vibration signal is really high frequency, and you will have it only when it is generated, whereas the other one is measured directly. So I think you cannot generate a cylinder pressure curve out of the vibration signal, right?
We can. So in the research project, this was one of our paths. We did some reconstruction of the cylinder pressure curve from the vibration signals. It is possible. It's also a kind of estimation. So it's not really a calculation, but it's, reconstruction. But for quality of the final result, so calculation of, let's say, the center of combustion or the NOx emissions, the better way was not to first calculate the cylinder pressure curve, and then if you have the curve, you can read out the center of combustion. But the better way was a direct estimation with some kind of frequency analysis, of course, of the vibration signal.
Okay, yeah, thank you. Well, do you need different engine operation ECU mapping for different fuels? If so, for a multi-fuel engine, do you need a kind of fuel detection sensor, or you leave the control and selection of correct engine operation maps to engine operation?
With this method, we have no experience regarding a real multi-fuel engine. We did not test that, for example, on a dual fuel engine up to now. But I think this will not be the problem. So if there will be any mappings, could be parameter mappings in the signal processing algorithms, then maybe it's just two different mappings, because the multi-fuel engines usually have two fuels, and so maybe it's necessary to switch over between these two. But would be interesting to get some real measurement results here.
Well, next one drills quite in detail. How does your software solution work? Are you using data-driven, physics-based, or mixed models?
Yeah, at the end, it's data-driven. So during the research project, we compared different chains of signal processing. We also used pure data-driven artificial intelligence methods, which had good results. But when we have worked long time with the artificial intelligence methods, then we learned a lot about the signal chain, and then we put in some kind of physical knowledge in our model chain. So at the end, by working purely data-driven during the project, we improved kind of, we call it gray box models. So it's a combination of some physical knowledge and data to calibrate the models, which gives then the signal processing chain. And for adjusting that to a specific engine type, or for comparing two positions on an engine type, then we go back to the data-driven. So because we have to calculate for different operating points, what are the results of the estimation. So we started pure data, did some physical modeling, and for application, it again will be data-driven.
Okay, thank you. Then next one is the center of if the center of combustion, the center of combustion can be changed by adjusting the equivalent ratio or ignition timing. I think, of course, this has a big influence, right?
Yes, of course, there are some operating points where a change of the ignition timing has no effect on the combustion, because maybe it's not possible to have early combustion, or if you have an engine running in self-ignition already, then you can do what you want with ignition timing. It has no effect, but usually this is just a one-to-one relation. If you advance the ignition timing, you see that directly on the start of combustion and also the center of combustion. And this is also important for adjusting the algorithms. We need that because usually on a typical small engine, we don't have the cylinder pressure indication system, at least not in the field engines. But then we can, let's say, play with ignition timing in each cylinder, and so adjust our estimation algorithms.
Okay, thank you. So next one is, can you detect combustion anomalies like knocking, misfiring, and/or pre-ignition?
Knocking, misfiring, yes. This is what we have been doing for maybe 20 years now without this method. Other anomalies, we did not check that. I suppose that detection of pre-ignition and really telling a system this was a pre-ignition might be difficult from the vibration signal. But I think for the application that we had in mind, this is not the real relevant case. It's rather the control case, so influencing each cylinder of the engine so that we can go to the limit of the engine, which with each cylinder, and so improve efficiencies, emissions. When it comes to very special combustion anomalies, I would have to check that, but I think it will be difficult because there is a long chain from the combustion chamber to the vibration sensor to be sure that this is now exactly the reason for that signal is a pre-ignition.
Yeah. Okay. You mentioned in your presentation that you have done the initial work on this engine at Karlsruhe University. Do you have meanwhile also other applications, so some more experience on that?
We checked the method on further engines, yes. For one of these engines or engine type, we also had very good results. Was also a rather small engine. We also did some checks for a large engine where we're still working on. The first results were not that good, but here we had no influence on the position of the sensors. So we were able to do some measurements on the standard knock sensor position. And we have some information about the other combustion characteristics. So of course, knock, we can see that. We also can do the estimation of the center and duration of combustion, but not in the quality that I have shown you today. And I suppose that, for example, for the other engines, this is the work that has to be done then with the sensor position, because we have seen that on the other engines really has the strongest influence on the results.
Yeah. Okay. Yeah. Would you see that when you installed it on another engine that you need also the cylinder pressure information first?
We need the cylinder pressure for the first engine of an engine type, because we need the reference. If we want to have a precision of, let's say, 0.5 degrees crank angle, then we need a good reference. We also need a second engine of this engine type, so a second, another engine, but the same type, to be sure that it was not a specialty of the first engine that we have seen. And also on that second engine, cylinder pressure indication will be necessary to have the precise reference information. And after that, we think that it is not necessary, because of course it's too expensive to machine all the cylinder heads for that. And for adapting it to each piece of that engine type then in the field, it's sufficient to be able to influence the ignition timing. So what we would need is an influence on cylinder individual ignition timings. Then we can do the adaptation of the algorithms. But of course, if we want to do something like cylinder balancing or really running an engine at the limits, then we also need cylinder individual ignition timings. For an engine which only has a global ignition timing adjustment, maybe we don't need this high-level combustion information.
Okay, I think then we got a lot of points, and thank you also for this extensive discussion.
Thank you.
Then I'd like to thank you and also Mr. Brünnet for the presentation and for the presentations and discussions. And I hope that the session today was helpful and of interest for all the participants. So I look forward to have similar discussions next year in Busan on the CIMAC Congress in reality, not only virtual. And so thank you very much for attending today. And now I hand over back to Mr. Schinke.
Thank you very much, Mr. Moore. You today were a wonderful host and guided the discussion fantastically. I think for all of our audience, it was a very interesting presentation today from both of our speakers. Also, thank you very much in the name of CIMAC for the two presentations. I now like to once again hint towards the upcoming conference in Düsseldorf, Germany, with regard to all topics around Power-to-X technologies. All experts will meet there and discuss all the ongoing topics with regard to that. And I, of course, want to announce the topic of the next Tech Talk special. The next Tech Talk will take place on July 12th, again at 2 p.m. CET. And we will have a mixed topic with some presentations about new engine developments and some presentation about fuels and lubricants. I'm looking forward to see all of you again, hopefully, at the next Tech Talk. And I wish you all a good afternoon. Goodbye.